You know, all around us, there are these unseen heroes making our modern world go round. I'm talking about electric motors. They're literally everywhere, powering the factories that build our cars and the systems that run our cities. For decades, they've been incredibly powerful, but let's be honest, not very smart. Well, that is all starting to change.
So that really brings us to the big question for today, right? How do you take these industrial workhorses, these powerhouses of manufacturing, and give them a brain? How do you actually teach an old machine new tricks and get it to think, learn, and adapt all on its own?
Okay, so let's get into it. And we are not just talking about abstract ideas today. No, we're going to use a real, step-by-step guide from Siemens, one of the biggest names in the game, as our blueprint. You should think of this less like a technical manual and more like a recipe for a revolution that's happening on factory floors as we speak.
All right, so where do you even start? Well, the very first thing you have to do is give the motor a digital identity. Before you can make it smart, the system needs to know exactly what it's dealing with. It's kind of like creating a character profile in a video game, setting up its stats and abilities, but for a massive industrial machine.
This whole process really breaks down into 3 simple steps. First, you identify the motor. Is its speed locked to the electrical frequency, what's called synchronous, or not? Then you punch in its vital stats. We're talking rated speed, power, all that good stuff. And finally, you set the basic rules of the road for how it should operate. Do all that, and bam, you've created its digital twin, and that is the foundation for everything else we're going to do.
So now our motor has its digital profile. It exists in the system. The next logical step is to connect it to the artificial intelligence that's going to act as its brain. And as the Siemens guide shows us, there are really 2 main ways you can go about this.
You've got 2 basic choices here, the global brain or the local reflex. The global brain connects the motor to a massive cloud platform, something like Siemens MindSphere. This lets it learn from the data of thousands of other machines all over the world. It gets smarter from the collective experience. On the other hand, the local reflex uses a small device right there on site for lightning-fast, real-time decisions. It's all about speed. Which one's better? Well, it really just depends on what that motor's job is.
Okay, the AI is connected. Now comes the most important part of all, the training. You can't just flip a switch and expect a genius motor. Nope, you have to send it to school. And its classroom, the factory floor itself. The AI has to learn from what happens in the real world.
So, how does this school work? Well, it all starts by recording at least 24 hours of super detailed data. We're talking everything: the different loads, the speeds, the shutdowns, the whole shebang. While this is happening, engineers are watching and manually flagging anything that looks weird, any anomalies. Then, that entire data set gets uploaded to the AI. That becomes its textbook for learning what's normal.
Now that big chunk of data isn't just used all at once. It gets split up. 70%, the biggest piece of the pie, is used for the initial training. That's what teaches the AI what a normal day looks like. Then you have 2 smaller 15% chunks. One is for validation, to check its work, and the other is for testing. You can think of it like a final exam, to make sure the AI really learned its lessons before it gets put to work.
Okay, so we've built the digital twin, we've connected the brain, and we've sent the motor to school. We did all that work. So, what's the payoff? What can a thinking motor actually do that a normal one can't? Well, this is where it gets really, really cool.
The first massive benefit is something called predictive maintenance. Because the AI has learned the motor's unique fingerprint for healthy operation, it can spot the absolute tiniest changes, a slight vibration, a small temperature shift, that signal a failure is coming. It can basically tell you, hey, I'm about to break down, long before it actually happens.
And the impact of that is just enormous. An unexpected shutdown on a factory line can cost a company millions. This just shows you how dramatically AI can slash those surprise failures. You stop reacting to problems after they happen, and you start preventing them before they start. Maintenance becomes proactive instead of reactive, and that is a total game changer.
All right, the second huge payoff is energy efficiency. An AI-powered motor doesn't just run at one speed, it learns to run optimally. It looks at the exact load it's handling from moment to moment and adjusts how much power it's using in real time.
And the result? A huge drop in wasted energy. The guide even points to specific settings, like parameter P1580, which is basically an AI-based eco mode that makes this happen. The motor learns to use only the precise amount of energy it needs for the task at hand, and not a single watt more.
So once you have these smart machines up and running, what does it look like day to day?
How do you manage them? Well, it turns out there are some new rules and new ways of monitoring that come along with all this new intelligence.
This table really sums it up perfectly. You've got health monitoring, where the AI is predicting failures. You have performance, where it's constantly fine-tuning itself. And you have energy saving, where it's adapting its power use. The key thing here is that each of these is a real function you can control, tied directly to a specific parameter in the motor's controller. It's not just an idea, it's a feature you can actually turn on and tweak.
Of course, with great power comes, well, a few new common sense rules. The guide lays out some really crucial best practices. For one, you always back up your configuration before you let the AI take over. You also need to keep a close eye on the machine while it's in that initial learning phase. And finally, you have to have a clear plan for how you're going to update these AI models down the road.
And all of this brings us to one final big thought. We've just walked through how a hunk of metal, a motor, can be taught to think, to predict, and to make itself better. This isn't science fiction anymore. This is happening right now. So the real question we're left with is this. When the fundamental machines that build our entire world can think for themselves, what does that change? The answer is probably everything. Thanks for joining me on this.